Hello, welcome to the next video in a playlist that I'm calling General Linear Models Design of Experiments. And here we're going to use R to illustrate the ideas of part 2 from one-way fixed effects ANOVA, estimating the parameters. Now in here it assumes that you've watched part 1, and part 1 is above here, and so I'm going to highlight it and I'm going to run it in a second, but we're going to look at a example from Montgomery, Design of Experiments, Analysis of Experiments. It's the third edition, example 3.1, where we look at the tensile strength of fabric. And so we create this fabric with different percents of cotton. So in one fabric it's 15% cotton, the other's 20, then 25, 30, and 35% cotton. And we want to look at the tensile strength. And tensile strength means how much force or pressure does it take to tear the material. And so I'm going to run that, and then that brings us to part 2, estimating the beta parameters. Now there, specifically, we were looking at estimable functions. And what that means, it's linear combinations of the betas that have a unique solution for an estimate. And in there, we looked at estimating mu plus tau 1. And I'll highlight it here. And so that means in the program it's L, but in the theory video it was lambda. So lambda prime beta, where lambda prime was 1100, and that way when you did the product it grabbed mu and tau 1, and those are what we wanted to estimate. Now just because we want to estimate it doesn't mean that we can uniquely estimate it. I mean, we have to determine whether it's estimable, and there we must show that it's part of the row space. Oh, and before I forget, I'm converting treatment. We created a data set called Tensile Strength Experiment. That's what TSE stands for. And in it, there's two columns. One is the tensile strength of the fabric, and then the second column we call treatment. And I'm changing it to a factor because we're going to need that later on when we look at contrast. So here we need to show that we can create a linear combination of the row space. So in the video I created P1, which is this, so it's 1 and then the rest zeros. And when we multiply that, transpose P1 x, it creates the lambda vector that we needed, 1, 1, 0, 0, 0, 0. Right? That's what we need to estimate mu plus tau 1. So from that point right there, we've shown that it's estimable. We get a unique solution. But some of the part I wanted to prove is that if you can come up with one linear combination, then there's an infinite number of linear combinations. And I also wanted to show this because even though there's an infinite number of possibilities, the solution is unique. And to me, that's just exciting. So I created a P2, or a row 2 in the video, and then I took row 2 times x, and it creates that lambda vector 1, 1, 0, 0, 0, 0. And then we created a row 3 and showed it generated the lambda vector, a row 4, and then a row 5. And all of these created, a linear combination of the row space that generates that lambda of interest. Then part of the uniqueness, or the estimability, is that the row that generates that lambda, even though there's an infinite number of them, if you take it times m, it creates a unique vector. All of these values will be the same. So there's row 1 m and row 2 m, and if you look at these results, they're 100% the same. Row 3m, row 4m, row 5m, they all generate the same value. And that's part of the uniqueness of the estimability. Now, in here, we're going to find unique estimates for mu plus tau 1, mu plus tau 2, mu plus tau 3. So we're going to create these lambda vectors, but here it's just L1, L2, L3, L4, and L5. And those are the ones needed to, when you multiply it times beta, it picks off the right parameters that you want to estimate. Now, to find the least squares estimate for that estimable function, we need the least squares estimate for beta, which in the video we call beta tilde. Here we call b tilde. And we take the generalized inverse of x transpose x times x transpose y. And that creates the least squares estimate for beta. And that's these values here. And because x is not full column rank, it ends up there's an infinite number of solutions for beta tilde. Now to find the least squares estimates, you take your lambda 1 times beta tilde, and that's the least squares estimate for mu plus tau 1. And this is the unique estimate for mu plus tau 2, tau 3, tau 4, tau 5. Now, what we showed in the video, these are actually just equal to the treatment mean. So this next function creates the means of each of the treatments. And let me scroll this up here. So this 9.8 was the least squares estimate of mu plus tau 1. But notice that it just equals the mean tensile strength for group C15, the group that has 15% cotton. And each of the other groups are equal to their means. And that's theoretically, we showed that's what has to happen. Now in here, in this video, we also delved into what we called a side condition. Now personally, I'm not a big fan of that side condition, but people use it, and so we're covering it. And so what I want to do is create a model that forces those taus to sum to 0. And that's what this option, contrast sum. And so if you were to look at that, it forces those beta parameters to sum to 0. And so let's look at that. And so we print the coefficients for this model, and it's this right here. Now notice we have 5 treatments, but we only printed 4. And that's because this is an over-parameterized model, the way that it works. So it has to drop one out, right? If they sum to 0, if we know the first 4, then we already know the 5th one because it has to sum to 0. So it leaves it out because of redundancy. And you'll see that this is indeed correct in a second. And so in the video, we showed that the mu parameter in this, when we use the side condition, is the grand mean. So we look at the mean of y, which is our tensile strength. It's 15.4, which is what the mu parameter is in this model where we use the side conditions, the tau sum to 0. Now in the video part 2, we showed that each of these estimates is the treatment mean minus the grand mean. And so to remind you, let's print the grand mean out, and that's what this is. Not the grand mean, the treatment means. And then we want to do that again, but we're going to just grab column 2 here and then subtract the grand mean from each of those, and we get this. Now notice when I scroll up here, when we printed the coefficients from this model where we forced the taus to sum to 0, notice that treatment 1, negative 5.24, treatment 2, treatment 3, or tau 4 I should say, and then this is tau 5, and those do sum to 0. Yep. Okay, well that's all I have for this video. In the next video we're going to look at partitioning the sum of squares in a one-way fixed effects ANOVA. So hopefully you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.